Okay, ji, Bismillah Rahman Rahim. Let's start over today's lecture. So today we have a lecture online. So today's lecture is related to the prestressed concrete. Prestressed concrete, and today we are going to study the shear design. So earlier we have done flexural analysis and flexural design. So today we are going to start with our new topic, that is shear design. So just before proceeding further, a brief introduction of the prestressed concrete, which we have been studying for almost like 6 weeks. So prestressed concrete is a particular form of a reinforced concrete which involves the application of an initial compressive load. So as we have studied earlier, that in prestressed concrete we apply the what you say initial compression load, which is your basically which produces the hog in the beam, negative you can say camber, and then under the application of the self-weight, superimposed dead loads and service loads, which produces the sag in the beam. So that produces, so these two moments, when they balance out, the beam will come to its original position. And if the service loads exceeds the camber, then we see the what you say sagging in the prestressed beam. So prestressed concrete is a particular form of reinforced concrete which involves the application of an initial compressive load, preloading before the application of the service loads on a structure to reduce or completely eliminate the internal tensile forces or stresses, and thereby controlling or eliminating the cracking. So the compressive force is imposed and it is sustained by highly tension steel reinforcement reacting on the concrete. The concept of prestressing of concrete is to introduce sufficient axial pre-compression in the beam, so all the tension in the concrete was eliminated in the member at the service loads. As we have stated earlier, that this pre-compression will produce the hog, negative camber, that is you can say tension at the top and compression at the bottom. Fine. And your what you say the applied loads, self-weight, superimposed dead loads, service loads, they will produce the sag. So in the case where we want to 100% eliminate the cracking, so in that cases we make camber, negative camber, and the moment due to the service loads exactly equal. And in the other cases where we allow some you can say cracking, in that cases the negative camber or the hog is lesser than the moment produced by the applied loads. Then we have studied that there are two types of prestressing. One is pre-tensioned concrete and other is post-tensioned concrete. In pre-tensioned concrete, we have studied like the precasting procedure is that in the first step, tendons are stressed between the supports. The tendons are stressed between the supports. Then the concrete is cast and cured, and in the third and the last stage, the tendons are released and the pre-stress tendons are released. You can see this, and what you say the pre-stress is transferred to the concrete, which results in the negative hog, which results in the negative, you can say, just a moment please, which results in the negative hog in the prestressed beam. In the second prestressing method, that is the post-tension concrete, in this you can see there is a hollow duct, there is a hollow duct and there is a tendon between this hollow duct. So first step is that the concrete is cast and cured. Concrete is cast and cured. Afterwards, the tendons are stressed, and then you can see the pre-stress is transferred to the concrete. Pre-stress is transferred to the concrete. Then in the third stage, the tendons are anchored. The tendons are anchored to the ends, and the duct in which there is a tendon that is grouted. So this is the three-stage procedure for the post-tension concrete. So now let's start. Over like lecture. Earlier it was a slight revision that what is pre-tensioning, post-tensioning, what is pre-stressing. So now shear design. So it is very much similar, apart from few differences. The shear design of pre-stressed concrete beams and pre-stressed and shear design of reinforced concrete beams. You can see it's very much similar, but there are few differences which along today's lecture we will discuss. So if you will have any question, you can raise your hand, and then I will answer your questions. In the MS Team, there is an option to raise the hand, and then during that, after that, I can answer your questions. So shear. Pre-stressed concrete beams normally contain shear reinforcement to ensure that the flexure failure, which can be predicted accurately and is generally preceded by obvious cracking and large deflections, will occur before the shear failure. So in different types of the failures which we studied in reinforced concrete and which we studied in pre-stressed concrete, that there are flexure failures and there is a shear failure. Flexure failure, we have under reinforced and over reinforced failure in flexure, and in which are, you can say, mostly preceded by cracking and deflection, so which gives us a warning before the failure. However, the shear failure on the other side is abrupt, and it's more difficult to predict accurately. So focus is to ensure that our pre-stressed concrete beam is strong in shear and it fails in flexure and not in shear. Why? The reason is that the shear failure is more abrupt, and it is you can say abrupt means that it gives you lesser warning as compared to the flexure failure. So pre-stressed concrete beams normally contain special shear reinforcement to ensure that the flexure failure, which can be predicted accurately and is generally preceded by obvious cracking and large deflections, that is, it gives warning before the failure. Whereas the shear failure, on the other hand, is abrupt and it is more difficult to predict accurately. So next point is that for the beams having rectangular cross sections, the variation of the shear stress through the depth of the member is parabolic. The value of shear being 0 at the top and bottom faces and reaches a maximum value at the mid depth. Just remember one thing, that the flexural stresses, they are maximum at the extreme fiber. So flexural stresses, their stress is equal to mi into phi, where m is the applied bending moment, I is your moment of inertia, and y is the distance from the neutral axis. So in case of the flexural stresses, they are maximum at the extreme fibers. Shear, on the other hand, its variation, flexural stresses variation is linear. The variation of the shear stresses throughout the depth is parabolic, and the shear stresses, they are maximum at the mid height or at the neutral axis, and they are minimum at the top and bottom faces. So for beams of I cross section, so in over, you know that in pre-stressed concrete we consider I section. So for beams of I cross section commonly used for the pre-stressed members, the shear stress increases abruptly at the transition from the flange to the web. So the shear stresses basically abruptly increases at the transition from the flange to the web. Reason is that the shear stress, if you recall its formula, it's VQ over IB. ठीक है जी? So when there is a transition from flange to the web, the width of the section is reduced and width is in the denominator. So when the width reduces, the shear stress increases. Shear stress increases. Let me show you one figure. So everyone can see this figure. This it is 5.3b. It's basically you can say it's shear stress variation in the I section. Everyone can see it. Everyone can see this.
Yes, sir.
So let me make one figure first. Let me add whiteboard. So I'm making I-shaped section. So let's say if this is the neutral axis, stress is equal to ठीक है जी. So stress is equal to mi over y, where this y is the distance from the what you say neutral axis. Now, in case of shear stresses, this is the flange part. In this, the shear stress is V Q over I into V. So shear stress is, this is the shear, applied shear. Q is the first moment of area. Q is the first moment of area. I is the second moment of area or the moment of inertia. And this B is the width of the section. So what happens? Guys, at present I am sharing this what you say whiteboard. I'm on the whiteboard, I'm making the figure so everyone can see the whiteboard.
No, sir.
Yes, sir.
If you are not seeing the whiteboard, it's basically because you are using the older version. In the newer version, because they have updated this, so I'm using the latest version. So in the latest version, you should be able to see this. So in this case, this B, so you can see this in case of the flange. This is the width. In case of the flange, this is the width. So when the width is large, you can see the shear stress is smaller. And over here, in case of the web, you can see this is the width. Now, when the width has reduced, it is how many of you cannot see the whiteboard? And those who can see the whiteboard can please raise their hands. Those who can see the whiteboard. So B is the width of the section. So at the junction, flange to web, you can see the width is drastically reducing because the flange has larger width, web has smaller width. So the shear stress is significantly, basically, you can say it increases. Shear stress basically significantly increases at the junction, and then it remains almost, you can say, constant because the width of the the width of the web is same. So the shear stresses, it depends on the width of the section. So shear stresses, they are maximum at the neutral axis, whereas the flexural stresses, they are maximum at the extreme fibers. Fine. So let's come back to our presentation. So let's come back to the lecture slide. Okay, so for the beams having a rectangular cross section, the variation of the shear stress through the depth of the member is parabolic. The value of the shear being 0 at the 0 being 0 at the top and bottom faces, ठीक है जी, and reaches a maximum value at the mid depth. For beams of I-shaped sections, which are commonly used for the pre-stressed members, the shear stress increases abruptly at the transition from the flange to the web because of the reduction of the section width. The stress distribution of I-shaped beam is characterized by a nearly constant value of shear throughout the depth, because in the web part, the width of the section is same. It remains same. It does not changes, and shear stress is VQ over I into B. V is the applied shear, Q is the first moment of inertia, I is the second moment of inertia. Only variable is B, the width of the section. Now, next is for I-shaped beams, maximum principal tension. Guys, if you recall in structural mechanics, we study that shear planes and principal planes. Principal planes are those planes over which we have maximum, you can say, normal stresses, maximum normal stresses, and the shear stress at the principal planes are 0. Over the shear planes, we have the maximum in-plane shear stress. And if you recall, in Mohr circle, we said that the principal planes and the shear planes, they are 90 degrees apart. And on the element, ठीक है जी, on the element, principal planes and the shear planes, they are 45 degrees apart. And we generally say that the shear is maximum at 45 degrees with reference to the longitudinal axis. So everyone remembers this point, that the principal planes and shear planes, they are 45 degrees to the one another on the element, and the shear is maximum at 45 degrees. So for I-shaped beams, the maximum principal tension will not be found at the neutral axis, where the shear stress is greatest. So at the neutral axis, the shear stress is largest, but near the junction of the web and lower flange, ठीक है जी, at the junction of the web and the lower flange. Basically, there will be two junctions. One is the junction of the web with the top flange, and other is the junction of the web with the lower part of the flange. So, near the junction of the web and the lower flange, where the shear stress is also high, but where the longitudinal compression is reduced by the effect of applied loads. Now, if you just keep one thing in mind, in case of sagging, you have tension at the bottom and compression at the top. In case of hog, which is basically your negative camber, you have tension at the top and compression at the bottom. ठीक है जी? So for I-shaped beams, the maximum principal tension will not be found at the neutral axis. At the neutral axis, the shear stress is greatest, but near the junction of the web and the lower flange, where the shear stress will also be high. Why shear stress will be high? Because at the junction, the width will be equal to the width of the web. ठीक है जी? And as we will move from that junction to the lower part of the flange, the width will increase, and the shear stress will reduce. So where the shear stress is also high, but where the longitudinal compression is reduced by the effect of the applied loads. Longitudinal compression basically means you have this pre-stressing, which is producing hog, that is tension at the top and compression at the bottom. And due to the applied loads, which is producing the sag in the beam, that is compression at the top and tension at the bottom. So they are basically cancelling. So that's what they are writing. But with the longitudinal compression basically produced due to the hog is reduced by the effect of the applied loads, which are producing the sagging in the beam. Everyone is clear with this point? Guys, if you have any question, you can ask me. Do not hesitate. Okay. Then it should be noted that the critical location for diagonal tension is diagonal tension. If you recall in your undergrad and MSc classes in reinforced concrete, it is very important that at what point from the face of the support you have the maximum shear. So we know that that you have mainly three types of the cracks. One are the flexural cracks, which are basically originating from the tension side when the tensile stresses exceeds the modulus of rupture, and they are almost vertical. Then the second type of the cracks, which are due to the shear, they are inclined at an angle of 45 degrees. Then there are what you say shear tension or flexure shear crack. Flexure shear crack, that is the crack which is basically you can say vertical at the start, and then it becomes inclined from roughly from the mid height. That is your flexure shear crack. So we will talk about these flexure shear cracks as well in short while. So it should be noted that the critical location for diagonal tension is usually not adjacent to the supports. So diagonal tension is usually not adjacent to the supports. You can see this diagonal tension crack. It is originating at some distance. So they are starting at some distance and they are maximum quite far from the support. So we actually want to know that exact location of this, that where this diagonal tension crack is maximum. So it should be noted that the critical location for diagonal tension is usually not adjacent to the supports, even though the net external shear is highest at this point at d/2 is highest there. The shear is highest at the distance d/2 from the face of the support. So critical location of the diagonal tension is usually not adjacent to the supports, even though the net external shear is highest there, because the longitudinal compression from the prestressing, because your prestressing is what you say resulting in the negative camber hawk. So there's what you say prestressing, even though the net external shear is highest there, because the longitudinal compression from prestressing is hardly reduced from its full value by the small external moment. So at these points, due to the prestressing, there will be compression at the bottom, and this is, let's say, simply supported beam. So you know that the moment at the supports will be very less, maximum somewhere here, but almost minimum here, maximum at the mid span, minimum at the supports. So the moment increases from the supports to the mid span. So at this point the moment is very less, small value. However, the pre-stress is for example, if we have a constant tendon eccentricity, the pre-stress value remains the same throughout the span. So at this point near the support, the compression due to pre-stressing, it's very high, and moments, that is the tensile stresses. Okay, moments will produce self weights, and superimposed dead load and service loads will produce what you say, the sagging moment, and which will be tensile stresses at the bottom. So tensile stresses are very small at the bottom and compressive stresses are very large. So because the longitudinal compression from pre-stressing is hardly reduced from its full value by the small external moments acting. ठीक है जी. So at the near supports, you can say the compression due to the pre-stressing is very large, and the tensile stresses or tension in the pre-stressed concrete due to the applied what you say service loads is very small. Everyone agrees to this point? Guys, can you hear me?
Yes, sir.
Okay. So it should be noted that the critical location for diagonal tension is usually not adjacent to the supports, even though the net external shear is highest there, because the longitudinal compression, so compression from pre-stressing is very high, that is the hog is very large at that point, and the what you say the tensile stresses or the tension due to the what you say bending, sagging is very small. So substantial longitudinal compression at the near support ends reduces the principal tensile stresses near the supports. In addition, vertical compressive stress, that is the support reaction from the beam, prevents diagonal cracking close to the supports. ठीक है जी? Agree or not agree? So I repeat, at this point, compressive stresses due to pre-stressing, they are very high, whereas tensile stresses due to the bending moment, which is the sagging bending moment, they are very small. ठीक है जी? On top of that, you have this vertical compressive stress that is produced due to the vertical reaction. So substantial longitudinal compression reduces the principal tensile stress near the supports. In addition, vertical compressive stress from the beam reactions prevents the diagonal cracking close to the supports. Consequently, diagonal tension crack. Diagonal tension crack for uniformly loaded, simply supported pre-stressed I-beam. ठीक है जी? So you have a very simple scenario here. You have a simply supported beam which is subjected to the UDL. ठीक है जी? So consequently, diagonal tension cracking for uniformly loaded, simply supported pre-stressed I-beams is likely to occur at about 1/4 of the span. 1/4 of the span. So shear is maximum near the support at distance d/2 from the face of the support. However, the diagonal tension crack originates from 1/4 of the span of the pre-stressed I-beam. ठीक है जी? So diagonal tension cracking for uniformly loaded, simply supported pre-stressed I-beams is likely to occur at about the quarter points of the span, where the net shear forces are relatively large, ठीक है जी? And near the junction of the web and the lower flange, where longitudinal compressive stresses are low and the shear stresses are high. Shear stresses are high. At the junction, why shear stresses are high? Because the width of the section is small, and the shear stress in the shear stress formula, width is in the denominator. So smaller the value of the width, larger will be the shear stress. So longitudinal compressive stresses are low and shear stresses are high. So everyone agrees to this. Can anyone explain what we are saying, so that I can understand that you guys are getting my point of view? Zuhaib, can you explain what we have studied so far?
Yes, sir. We are studying shear in the pre-stressed beam. So shear is maximum at the top flanges and
Shear stress, flexural stresses, they are maximum at the top and the bottom flanges, because your distance y from the neutral axis is maximum. The shear stresses, they are basically minimum at the ends, and it's maximum at the mid height. The reason is that the shear stress is equals to VQ over IP, where V is the applied shear, Q is the first moment of area, and Q is the second moment of area. The variable is B, which is in the denominator. So smaller is the width, larger will be the shear stress. So width of the web part is smaller, so you can see the shear stress is larger, and in the web part the shear should be almost constant, because the width is fixed. So I repeat, for I-shaped beams, for beams of I-shaped section commonly used for pre-stressed members, the shear stresses increases abruptly at the transition from the flanges to the web. Why? Because the width of the section reduces. When the width of the section reduces, the shear stresses will increase, because the width is in the denominator in the formula. So for beams of I cross section commonly used for pre-stressed members, the shear stress increases abruptly at the transition from the flange to the web because of the reduction in the section width. The stress distribution of I-shaped beam is characterized by a nearly constant value of shear throughout the depth of the web. So in the web part, the width is constant, although it is small, but it is constant. So you will have large shear stresses in the web part. For I-shaped beams, the maximum principal tension will not be found at the neutral axis. Why? Because we know that principal stresses, they are maximum over the principal planes, and over the shear planes we have maximum in plane shear stress, and over the shear planes we have average, you can say, normal stress. We have average normal stress. And over the principal planes you have the maximum normal stresses, and you have zero shear stresses. So for I-shaped beams, the maximum principal tension will not be found at the neutral axis. At the neutral axis, your shear stress will be greatest or the largest. But near the junction of the web and the lower part of the flange, ठीक है जी. So at this junction where the shear stress will be high, ठीक है जी, but the longitudinal compression will be reduced by the effect of the applied loads, because your pre-stressing is producing a hog in the beam, which is producing a compression at the bottom. Your applied loads, that is producing a sag in the beam, that is producing tensile stresses at the bottom. So larger is the applied service loads, the larger will be the tensile stresses, so they will cancel out your compressive stresses due to the pre-stressing. So near the junction of the web and the lower flange, where the shear stress is also high, but where the longitudinal compression is reduced by the effect of the applied loads. It should be noted that the critical location for the diagonal tension is usually not adjacent to the supports. Why not adjacent to the supports? Although the external shear is highest there, the reason is the longitudinal compression from the pre-stressing is very large, ठीक है जी, and what you say, longitudinal tension from the bending moments is very small. So substantial longitudinal compression, ठीक है जी, large values of longitudinal compression from the pre-stressing reduces the principal tensile stresses, ठीक है जी, principal tensile stresses near the supports. In addition, vertical compressive stress from the beam reactions prevents the diagonal cracking close to the support. So your diagonal tension crack is approximately 1/4 of the span, ठीक है जी, so from the face of the support, ठीक है. Although shear is maximum here, but you know that compressive stresses due to the pre-stressing are very large, and the tensile stresses due to the what you say applied loading, they are very small here. So your diagonal tension crack will appear where you can say your this tensile stresses, their value will increase. As we move from supports towards the mid-span, your bending moment will increase. As you know that at the, for simply supported beam, at the supports we take the moment as 0, and at the mid-span we take the moment as WL square over 8. So consequently, diagonal tension cracking for uniformly loaded, simply supported, pre-stressed I-beam is likely to occur at about quarter point of the span, where the net shear forces are relatively large, ठीक है जी, where the net shear forces are relatively large, and near the junction of the web and the lower flange, where longitudinal compressive stresses are low and shear stresses are high, ठीक है जी. So this is in the figure they have shown. This is your I-shaped section. This is your shear stress distribution. So you can see the shear stress distribution. It increases. It is minimum at the ends, and it is maximum at the mid-span. And you can see from where the web is starting. In the web, the shear stresses, their value remains almost same because the width is same. But at the junction, you can see a significant increase in the shear stresses, because you can see the flange width is significantly larger than the web width. So as we proceed from the flange to the web, the width reduces significantly, so the shear stresses increases significantly. ठीक है जी. So everyone agrees to this point. Then this is your flexure stress variation. So you can see The flexural stresses, they are minimum at the neutral axis and they are maximum at the extreme fiber. So flexural stresses, they depend on the distance y from the neutral axis. So as that distance increases, your flexural stress increases. Moreover, this shear stress variation is parabolic and the flexural stress variation is linear. ठीक है जी? And you can see over here these two lines, basically they are showing you what you say, the hogging and sagging. At the midspan, at the midspan, there will be sagging. So the tensile stresses, ठीक है जी? At the bottom you will have let's say tensile stresses, and at the top you will have compressive stresses, and in the supports, near the supports, you have the hog. In the hog you have what you say compressive stresses at the bottom and tensile stresses at the top. So these are basically your flexural stress variation, and this is the diagonal tension crack, which they say that the diagonal tension crack originates at about 1/4 of the span. Okay, from 1/4 of the span. Now comes over more relevant, or the thing which we are going to discuss today is flexural cracking. ठीक है जी? Then we have flexural shear cracks. We have then web shear cracks. So these are the three types of cracking on which we will focus today. And our shear design is based on these two types of cracking. So diagonal cracking shear. So diagonal cracking shear extensive testing has shown that two types of diagonal cracking can occur in pre-stressed beams. ठीक है जी? So one is flexure shear crack. The second is web shear crack. ठीक है जी? As I have said earlier that what you say, shear stresses, they are maximum at the mid height, and flexural stresses, they are maximum at the extreme fibers. And you can see over here in this figure 5.5a, you see the beam is subjected to the what you say service loads. So service loads producing the what you say sagging in the beam, and in this sag you can see the tensile stresses will be at the bottom and compressive stresses will be at the top. So the flexure cracks will appear once the tensile stresses exceeds the modulus of rupture. Once the flexure stresses becomes greater than the modulus of rupture, the flexural cracks, which are almost vertical, they will originate and they will start moving towards the compression side. From tension side they will originate and they will move almost vertically towards the compression side. The second type of the cracking is the web shear. So we know that the shear is what you say maximum at the close to the face of the support. ठीक है जी? Why at the face of the support? Because compressive. ठीक है जी? Because what you say in case of the pre-stress, what you say compression hawk produced by this you can say pre-stressing, resulting in compressive stresses at the bottom. The compressive stresses are high and the moment at the near supports is small. ठीक है जी? Moment is small, so resulting in smaller tensile stresses. Fine. So the shear is based on over what you say structure mechanics, that shear is 45 degrees, maximum at 45 degrees with respect to the longitudinal. So these are the web shear cracks which are approximately 45 degrees to the longitudinal axis. So we have flexural cracks and we have web shear or shear cracks. Then the second or third type of crack is your flexure shear. So if you see over here, flexure shear crack is that initially it's a flexure crack and then it becomes the shear cracks. So initially it was almost, you can say, perpendicular to the longitudinal, and then it converts into it merges into the shear. And this type of the crack, we call it as the flexure, initial part flexure and this part shear. So this is flexure shear cracks. Flexure shear cracks generally we see near the face of the support, from here, this side, and at the mid span we generally just have the flexural cracks. So over today's target is to design the pre-stressed beams so that they are safe in shear, because shear is shear failure is abrupt, and gives, when we say abrupt, it means it gives lesser warning, whereas the tensile failure is more ductile, gives a warning before the failure. So we want to design, shear design is based on this flexure shear cracks and web shear cracks. So this web shear crack, which is purely based on the shear stresses. This flexure shear crack, which was initially originating perpendicular and then it becomes inclined. So this is your flexure shear crack. So over shear design will be based on the flexure shear cracking and the web shear cracking. So things are clear up to this point. Things are clear up to this point.
Yes, sir. Yes, sir.
So over shear design will be based on this flexure shear cracks and web shear cracks. Flexure shear cracks and web shear cracks. Web shear cracks are your pure shear cracks. Flexure shear cracks, that at the start they were flexure, they were perpendicular and then they become inclined. So this crack will be your flexural shear crack. Now, flexural shear cracks occur after the flexural cracking has initiated or has taken place. The flexural cracks extends more or less vertically into the beam from the tension phase. So flexural cracks will originate from the tension side. Because of the application of the service loads, there will be large bending in the beams, and at the bottom you large bending, that is sagging in the beam. At the bottom you have the tension. So when the tensile stresses becomes greater than the modulus of rupture, the flexural cracks will appear, and these flexural cracks extends more or less vertically into the beam from the tension phase. When a critical combination of flexural and shear stresses develops, critical combination of flexural and shear stresses, flexural your vertical cracks, shear your inclined cracks, develops at the head of the flexural crack. That crack propagates in an inclined direction, inclined direction, but there is a difference in their inclination, so often quite flat. Now if we see over here, this is the web shear crack. The web shear crack is almost 45 degrees to the
यार क्या हुआ, मेरे ख्याल में सर लेफ्ट कर गए हैं।
क्लास एंड हो गई है।
एंड तो नहीं हुई, सर लेफ्ट कर गए हैं।
Can everyone hear me?
Yes, sir.
ओके थोड़ा सा ना मुझे हेल्प चाहिए होती है कि जब बता दिया करें क्योंकि एट 10 o'clock इंटरनेट वाज डाउन सो वो फिर जो है ओके जी सो लेट मी